So for those of you who are planning to pay attention to this tutorial, if you want a copy of the slides, I put the PDF in the directory, the inference directory in the GitHub repository. You might also notice that my voice is a little bit shot after last night's karaoke outing, so thanks to all the people who came to that. There's also a subdirectory in the inference directory called nested sampling code, and that has just a couple of files in it that implement the things I'm going to demonstrate, and hopefully they should run for you. Unfortunately, they're not in a notebook because I don't know how to use notebooks yet. So I thought to demonstrate nested sampling, well, I'll get into what nested sampling is and what problem it solves shortly, but to keep things concrete, we'll look at a fairly typical data analysis example. And this is some clearly fake data that we're measuring perhaps the transit of an exoplanet in front of its star, and the brightness over time has this dip. And in a very idealized situation, you might want to treat this as a curve fitting problem and infer something about the depth of the curve and the other parameters that might describe what's going on here. You might also notice that this y-axis is kind of arbitrary. I don't think any transits are really going to change brightnesses by 5 magnitudes. And also, if this was magnitude, the transit is making the star brighter because the magnitude is going down. But anyway, this is just a curve fitting example. We've been fitting a lot of straight lines in the last couple of days, and this is something a bit fancier than a straight line, just for a change of pace. So this kind of curve fitting family of problems is related to heaps of data analysis problems in astronomy. So obviously you could think of a much more realistic version of this, and there are people in this room who work on that. There are lots of problems that look like curve fitting in studies of spectra. So if you're trying to find emission and absorption lines, or fit the continuum, or infer some parameters from a spectrum, then that's a curve fitting problem of sorts. Even the task of finding stars and galaxies in an image and trying to locate where the stars are, that's a curve fitting problem as well. It's just that the image is your curve. It's a curve. Two-dimensional version of a curve. So there's lots of problems that look like this. It's a good kind of archetype to work with. So the truth that I generated this data set from is given here. So that function was just 2 values, and there was a time window over which it was the low value, and for the rest of the time it was the high value, those with 10 and 5, and the times of the changes were 2.5 to 4. This kind of model also appears in other contexts. Statisticians like to call it change point models, where you have anything that's constant for some amount of time and then changes to another constant, and you don't know when it changed or to what new value. It's called a change point model. And I added noise. I generated noise from a Gaussian distribution. So when I had the numpy array y with the red values in it, I just added random noise with a standard deviation of 1. Okay, so in reality, if we had this data set, we wouldn't know the values of all these parameters, or we wouldn't know what this curve was. That might be something that we want to infer. Or we might want to infer something like the size of the planet or things like that. And we could have a model with unknown parameters and interpret our problem as an inference problem for these parameters. So what we'll do today is we'll fit this data set with a model like this, that there's some time tc which defines the center of the transit, and there's a width w which defines the width, and so when the time is between center time minus half the width and center time plus half the width, then the curve has 1 value, And when it's outside of that range, the curve has some other value. So this model has 4 parameters, A, B, T, C, and W. So 4 parameters. And we would want to infer those from the data set, which could be these noisy blue points. Yeah.
Can you go back to your parameter? Yeah.
Yeah.
Is there a particular reason why you made this A to A minus B and TC minus W over 2, TC plus W over 2, as opposed to A, B, and is there a reason you parameterize it this way?
Not really, just okay. Kind of my aesthetic habits. You could parameterize it in different ways. So you could do it A and B as being the 2 levels, as opposed to doing it by 1 level and the difference. And you could define it from the beginning of the transit as opposed to from the middle. I think the one thing I would say that might constitute general advice is that with A minus B, defining this lower level of the curve as A minus B instead of just another constant B makes it easier to assign, I think, sensible priors for A, joint prior for A and B. Because if you did something where if you had A here and just B here and you just had 2 levels, and you write down a simple prior where A and B are independent, then you're saying that A and B they don't have anything to do with each other, and that's possibly a bit unrealistic. Usually you would expect the lower level to be somewhat close to the top one. So parameterize apply the difference. Okay. So in the Bayesian framework, which we've been using for the last 2 days, inferring the values of these 4 parameters from data just corresponds to calculating the posterior distribution for these 4 parameters A, B, T, C, and W given the data D. And that's proportional to the prior distribution, or it's equal to the prior distribution for the 4 parameters times the likelihood function divided by the marginal likelihood, which is not a function of the parameters. And this marginal likelihood, which Phil was calling the evidence, I tend to say marginal likelihood, but they're exactly the same thing. Marginal likelihood, Bayesian evidence, FML. There's actually even more names like the prior predictive, because it's the probability of the data set before you got it. I'll probably just say marginal likelihood a lot, so just bear in mind that it's exactly the same thing as the evidence. And that's just the constant that normalizes. If you have the prior times the likelihood, you need to normalize it to make it a posterior, and so this is just the integral of the numerator over the parameter space. So integral of prior times likelihood over the entire parameter space. To get going, I'll just choose some priors, and these are very much convenience priors, not putting too much effort into describing prior knowledge accurately. So for A, I'll just use a uniform distribution between minus 100 and 100, and A was the brightness level not in the transit. B was kind of the depth of the transit, and I'm just assigning a uniform distribution from 0 to 10. TC, the time of the middle of the transit, I'm assigning a uniform between Tmin and Tmax, and those are the limits of the data set. And the width, I'm also doing uniform between 0 and the length of the data set there. So this is again this notation where you can communicate your assumptions pretty quickly if you know how to read the notation. So the parameter, twiddles, and then its prior distribution.
Can you briefly discuss uniform from minus 100 to 100 versus log?
Yes. So in this case, okay. So it would depend for starters, whether A could possibly be negative. So here I've written on the y-axis magnitude. It's not really magnitude, but magnitude can be negative. So to use log magnitude wouldn't really make sense. And
well, I mean, now this actually brings up a good point, which is that what are your flux units actually in?
Yeah, they're nothing. They're made up. So.
But so in your fake, what is your fake data set goes from 5 to 10?
Yeah.
So, but you did your prior from negative 100 to 100. So
Yeah.
so you're giving a lot of buffer.
Yeah, so this is like saying, so our data set, just looking at it, you can see A is 10, right? But before knowing the data, I would have had a lot less of an idea about the value of A. I may have suspected that it could go anywhere from -100 to 100. If this was a real astronomy problem, that's way too wide of a range.
Okay.
Yeah.
But it, I mean, even if it's a real demonstration problem, it still seems like too wide of a range.
Yes, I think, yeah.
Sorry, this is worth discussing because choosing the priors seems like it's one of the hardest things.
Yes, it is. I don't know why I went -100 to 100, actually.
Okay.
I think maybe I'm... another way to think of it sometimes is when I'm writing a code and I put in a certain prior in my code, that's the kind of... It tells me something about the data sets for which I expect the code to work okay.
Okay.
So for example, if my prior was much more informative and A could be between only like 0 and 20, and then I plug in a data set with 50, I shouldn't be surprised that it's not going to work.
Yeah, but sorry, just
Yeah.
but shouldn't I choose the prior, put my prior knowledge? So if I look at this here, I
Yeah.
know that the model, the only way to move up and down the model is with A.
Yeah.
So I really can say that even if I want to be careful, I can say A is between 8 and 14, and then so shouldn't when
But
I'm actually doing this.
It depends on whether you knew that before you saw the blue points.
Okay, but I mean, this is a question. Like, if I'm not talking about writing a general code or anything.
Yeah.
Now I want to do this. I want to get that model there.
Yeah.
Can I look at the points and then choose the priors looking at the points given the model that I have in mind?
Yeah. Is it wrong to say that the prior is from 0 to 15?
No.
Okay.
No. And you'll just get your results, and there'll be the results that come out of a prior that's from 0 to 15.
But in some sense, you'll have a meaningless then evidence interval.
Less
Because
meaningful.
if you looked at the points and you decided to put this range on A, it's
Yeah.
true it won't change the shape of your posterior because clearly A has to be inside this range.
Yeah.
From the likelihood. But it will change, it will have a very strong effect on your
A
evidence.
fairly mild effect.
Okay.
Factor of a few.
No, because you went from -100 to 100.
So a factor of 10.
Right.
Factor of
Which-
10 is not much.
Well, it was enough to change the answers in Phil's calculation.
That's because he had a very close...
But if they were
Situation.
close, you don't need to calculate the evidence, it's obvious.
We'll discuss that.
So which method can you give what your opinion of the pros and cons of the two different methods? A logically an astronomer informed prior or versus this more generic prior?
You talking to me?
Yeah.
Well,
I mean, you told me that something.
I don't believe there's any way for most parameters, for most inferences, that anyone has a prior belief. For most parameters in most inferences, I don't think anybody has a prior belief. Really, not a well-established prior belief.
I just looked at my data and I saw that the flex
That
rate.
would be a posterior belief if you looked at your data.
Just tell me what we should do in real life.
I don't know.
God damn it.
I haven't...
Why the fuck are we here
What I do know is that posterior probability distributions don't depend very strongly on this choice. So then you
Okay.
can do whatever you like. What does depend very strongly on the choice is this Bayes factor, and that's.
Okay, just remember what I said. Pog just said it depends very strongly, but keep in mind that it depends even more strongly on the goodness of fit. So models that have high accuracy will win in evidence comparison, I think,
Yeah.
for reasonable variations in priors if you're going to go down that route.
But
Also
it's
remember,
noticeable that that can be determined just by the maximum likelihood value. Right?
Can I maybe I can I don't know what conversation you're having. I can't tell.
Right.
If I'm a referee and I see this paper and they've chosen this prior distribution, is that okay?
Can I throw out an answer?
Good.
And I'm surprised no one's saying it. Like, I mean, you should be doing on the Bayesian side. All of these things. You should be doing sensitivity analysis where you try a few priors. Uniform one, whatever. One that I haven't heard mentioned is what's called the reference generative model for data given parameters, and there's a procedure which you can use, or Jeffrey's prior is like a special case of this, where without looking at the data, you can come up with a prior which is basically related to how much you think you're going to learn once you actually observe the data. So, so it's a objective Bayesian prior. It's not subjective. You may or may not like it for lots of reasons, but it is a well-posed one. And if you're going to do a sensitivity analysis, certainly a good one to choose. So, so I think if you wanted to do best practices, try a few, and probably some objective prior should be it.
Okay, so for those following on the internet, we had a big discussion about choosing priors. Oh, people can hear everybody? Oh, that's good. Awesome. So despite being in a tutorial teaching you how to compute marginal likelihoods, which are quite sensitive to the choices of priors, I actually didn't want to focus too much on the choices of priors. I have a hack actually that no one has, one person talked to me about for about 5 minutes, and the purpose of the hack was actually to just maybe get together in a small group and read the literature on what's called elicitation, which is a process by which a statistician who knows how to implement Bayesian calculations interviews an expert about whatever the calculation is about, so stars or whatever astronomical thing you're doing, in order to come up with a good model of their prior beliefs, based on questions of along the lines of, how surprised would you be if this extra data set came along and you learned that the value of the parameter was between 5 and 6, and then the expert says, oh, that would be extremely surprising. And then the statistician would say, okay, that's a constraint, that whatever prior we have to assign has to be, extremely surprising, that it's between 5 and 6. So there is quite a lot of literature, and it's a little bit interesting psychologically, actually. There are certain questions that can lead to not very good assignments of priors, and they try and avoid those questions and ask questions about quantiles of the distribution or something. So where should the quantiles of my prior be? So if I'm thinking about this parameter A, and I could try and think of an interval where I think there's about 50-50 whether the parameter is in that interval or not. So if it's a magnitude of a particular kind of star or something, maybe it's maybe I think that 15 and 16, between 15 and 16 is about as likely as outside that range. And then any prior you write down should satisfy that constraint. Okay. It's a hard problem. It's the problem. Or there are two problems. As Phil said, there are two problems. There's one is how do you assign priors, and the other one is how do you compute integrals. So the other thing I wanted to just point out here with this prior for these two kind of time axis related parameters is that I've actually used something that would come in a data file in order to assign those priors. It seems like I'm using the data to assign those priors. But as we've seen in a lot of the curve fitting examples that we've looked at, there's a distinction between what's the data in the sense of having a sampling distribution assigned for it, and that would be something that in a PGM would have the double circle, and what's prior information that's given as a dot. And usually, in the way most people write down models, the x-axis, or in this case the time axis, is actually part of the prior information, even though it might come in a file data.fits, or in my case data.text. So I'm just going to go ahead and make standard assumptions. Sampling distribution, I'm going to assume Gaussian noise, which is very common for noise models. So the sampling distribution for the data, for all the y's, is a product of n terms, each of which is a Gaussian, and the mean of the Gaussian is given by the model function. In this Twiddles notation, you could write this down as yi get conditional on all the parameters, so you can add conditional on things to this notation. Twiddle's a normal distribution, and n stands for normal. The mean of the normal distribution is this function, which is just the shape of the model I'm fitting, and the variance, which is annoying, is sigma I squared, where this is the size of the error bars in the data set. Now, it's just an annoying thing that the convention is that the second argument to a normal distribution in this notation is the variance, or standard deviation squared. But if you just write it with the squared, then like if this was standard deviation of 10, you would just write 10 squared. And then you've technically written the variance in there, so you satisfy the convention, but you also satisfy readability because you just look at it and you see 10, and that's the standard deviation, which is more intuitive. Okay. So instead of just doing an MCMC method to explore the posterior distribution for these 4 parameters given the data, I'm going to discuss nested sampling, which is an alternative method, and it does 2 things. Instead of just sampling the posterior, it samples something else, a sequence of probability distributions, that the first of which is the prior. So you start by sampling the prior, and then you do some stuff in order to go uphill towards the peak of the likelihood function. And by doing this, you get posterior samples, so you can get the same output that you would get with just standard MCMC, but you also get the value of the marginal likelihood. So if you want to do model selection of this model that you're fitting now and some other model, you've already got the marginal likelihood when you do your fit. You don't have to do an extra calculation when you decide to do another model, to compare it with another model. Nested sampling is very popular in astrophysics. It's one thing where we're ahead of the curve. Statisticians haven't paid a lot of attention to it, which I think is a little bit of a mistake, because it has some unique strengths. That there are some advantages to it, and there is a certain class of problems where nested sampling works and many common alternative techniques don't work. And I'll talk a little bit about those. Okay. So the nested sampling algorithm was invented with the marginal likelihood in mind. John Skilling wanted to be able to calculate the evidence. And the reason is to do model selection. So if, for example, our transit model was called M1, and there was some alternative, perhaps with different parameters, called M2, then if we want to calculate the posterior probabilities of M1 and M2, we would have to go through this intermediate step where we get the likelihoods for those, which is the probability of the data given M1. This is the probability of the data given M1, but not given its parameters. And the integral, this is given by this integral, which is the integral of the prior times the likelihood over that model's parameter space, which in the context of the parameter estimation problem of θ1 given the data is the normalizing constant on the bottom of Bayes' rule. So if you have these 2 normalizing constants, then you have these 2 likelihoods, or marginal likelihoods. So if you have these 2 marginal likelihoods, you can do what's called Bayesian model selection, which is really you can just calculate the posterior probabilities of model 1 and model 2, or their ratio. And we had a little bit of a discussion with Phil's presentation about terminology. This ratio of likelihoods here, or ratio of marginal likelihoods, is called the Bayes factor. And this version of Bayes' rule, which is you can just get by writing down a Bayes' rule for this and a Bayes' rule for that and dividing the 2 equations. This ratio is just called the posterior odds, and this ratio is just called the prior odds. And this quantifies how likely M1 is compared to M2 given the data, and not given the data, and then given the data. So it's just in a different scale, a different way of measuring the same thing. Instead of saying that the probability of model 1 is 2/3 and the probability of model 2 is 1/3, you could say that the odds ratio is 2/1 or 2. So nested sampling will be able to give us this for a model, and also the posterior distribution, posterior samples. There's another motivation for nested sampling, which is one that actually I find more compelling, and that is that there are many problems where MCMC doesn't do very well. And so I've made a little smiley face, kind of two-dimensional posterior distribution that I just made up. In data analysis, it's kind of unlikely that you're going to get something this complicated, but it can happen. There are some problems that are notorious for having multimodal solutions, such as when you're fitting sinusoidal things to gappy data, and in the kind of Fourier analysis you get aliases, corresponds to multiple peaks in the posterior distribution for a frequency, for example. So if you had this posterior distribution here in 2 dimensions, or even the analogous thing in higher dimensions, then you'll experience a difficulty with this degeneracy here. Because if your particle is walking around exploring the space, the narrow width of this distribution will prevent it from moving very far. So it'll take a long time to kind of diffuse from this end of the curve here all the way along the degeneracy down to the other end of the curve. And you really want to be able to sample it all so that your results are correct. Another difficulty is multiple modes. Just like optimization methods get trapped in local minima, so does MCMC gets trapped in local maxima. So if you're exploring this mode here, in principle you want to be able to jump across this valley and explore here and jump back so that you can quantify the amount of probability in these 2 modes. But in practice it might take about 100 years for the walker to escape out of here and go through this valley, because this valley by definition has low probability. So it will take a very long time for you to see your MCMC results jumping from one mode to the other and back. Now there's a third problem that also causes difficulty, and it's uncommon, but it does exist, and that's called a phase transition. And what this is you can have a single mode. So this part on the right here has a peak, a narrow peak on top of a kind of broad plateau here. So this can be entirely unimodal, this peak here, but there's a high volume but low density component with a low volume but high density component on top of it. And the problem that happens here is if you imagine doing the Metropolis algorithm and you're currently sampling in the kind of narrow peak part, if you propose a move that takes you out of that into the plateau, then the acceptance probability for that proposal will be very low, because the ratio, there's a big ratio of densities. So if in high dimensions it can be that the ratio of densities is like e to the power of 50 or something like that. So you'll never, if you're in the narrow component, you'll never see the broad component. And it might be that both of these are important and you need to explore both of them. On the other hand, if you have a walker that's walking around in the plateau, eventually it should, spend some time inside the narrow peak. But that also would not happen in practice if the ratio of the densities and the volumes is very large. Because in order to get from the plateau into the narrow component, you have to propose to go in there, if you're thinking in terms of the Metropolis algorithm. And if the volume of that thing is so tiny, the chance that you're going to generate a proposal that goes into it is really low. It could be, if the ratio of the densities is like e to the power of 50, the ratio of the volumes might also be e to the power of 50, and that will never happen in practice. So there is a situation, and it's not very common, but it does happen, where you can have a unimodal posterior distribution that you still can't explore correctly, and it kind of behaves like a bimodal one, because it's like, instead of the 2 components being separated in space, they're kind of separated by a weird volume density contrast thing going on. So one advantage of nested sampling over just standard MCMC is that, well, firstly, the problem of phase transitions is completely solved. The problem of multiple modes and strong correlations is never completely solved, but it can give you a better chance of getting decent samples than just running an MCMC. So when I discuss the method, I'm just going to introduce a change of notation, which is common when people go from discussing Bayesian models and priors and likelihoods and things, and they go to start talking about computational methods. There's usually this change of notation. So the parameter space, we're still going to call the parameters theta, but instead of writing out probability symbols like this for the prior and likelihood and the marginal likelihood, we sometimes just write the prior as pi of theta, and the likelihood as L of theta, and the marginal likelihood as Z. So numerically, we're going to look at a method for doing an integral of this form, pi of theta times L of theta. Now when you look at this, this is what's called an expected value. An expected value is any integral that's an integral of a probability distribution times a function. And the standard Monte Carlo way to do that is to just generate samples from the distribution and calculate the average value of the function. And if you try to calculate the marginal likelihood that's exactly what Phil was doing at the end of his tutorial. Sample this, average that, and that's a Monte Carlo estimate of Z. The problem in practice is that the likelihood function might have a peak that's in a very small volume of parameter space that ultimately will dominate this integral. And if you do a finite number of samples from the prior, you probably won't go into this very small region where the likelihood is really high that dominates the integral, and you'll probably underestimate the integral. So what nested sampling does is it tries to it's a way of doing this integral that is more effective than just sampling from the prior, and it does that it starts by sampling the prior, but then it eventually cuts down the volume of the space that it looks at into smaller and smaller volumes, and it has a fancy way of doing something that results in the same value of the integral. So one way to get a handle on this is to imagine you just had a single parameter, x, with a uniform prior between 0 and 1. So that would just be a flat line on here. And a likelihood function that was monotonically decreasing. So this likelihood function given by the black curve. Now in that case, the integral to get the marginal likelihood would be quite easy. It's just the integral under the curve. Integral of prior times likelihood, and the prior density is just 1. So it's just the integral of the likelihood. And you get this area there would be the marginal likelihood. Okay, if we had a one-dimensional problem, that would be easy. We don't have a one-dimensional problem. We've got a four-dimensional problem, or we might have a 1,000-dimensional problem. However, if we were looking at the one-dimensional problem and we were able to generate some points on this curve, like these black points, we would be able to approximate the integral by doing some kind of just numerical quadrature with those black points. So even if we were looking at our 1D problem and we had not the whole curve but just a few points, we could get a decent approximation of that integral just using trapezoidal rule or something like that. And the key insight of nested sampling is that actually, even though we have a 4-dimensional problem, or maybe a 100-dimensional problem, or a 1,000-dimensional problem, there is a way of looking at any high-dimensional problem as having a graph like this associated with it, whose integral is the correct marginal likelihood, even doing the average over the higher dimensional space. So our 4-dimensional transit fitting problem implies a curve like this, and if we can calculate points along the curve that's implied by that problem, then we can numerically do the integral, and that's what nested sampling is all about. And if this is a bit tricky, just to dispel any imposter syndrome, the nested sampling paper came out in 2004, and it seemed important to me, so I tried to read it, and I didn't understand anything. And I think I first understood it in about 2008. So I think some presentations of it are a bit easier to understand, but the original paper is fairly difficult. So don't worry if you don't get it the first time. So this is a plot taken from the original nested sampling paper where it's showing the parameter space, or a two-dimensional example of a parameter space here. In our example, we'll have 4 dimensions. And here we've got a plot that's like my plot there, where the structure of our problem here has a curve like this associated with it. And I'm now going to define how this curve is defined and how we get points along it so that we can do the integral. So if you imagine taking the parameter space, just imagine for argument's sake that there's a uniform prior in the parameter space. You could imagine ordering all the points in that space from lowest likelihood to highest likelihood. Okay. So somewhere in your space there's a point of maximum likelihood, and we're going to label that point by how many, or what fraction of the space is it worse than in terms of likelihood. And the highest likelihood point by definition is worse than no other point. So it has a rank, if you like, of 0. No points in the space beat it.
Wait, sorry, a point in a space has measure 0, so what?
I'm just glossing all over that. Do you want me to?
It seems important, but
it ends up not being important at all.
Okay.
We can discuss it afterwards if you want to discuss the technicalities.
Okay.
Okay.
I don't want to derail anything.
Sorry?
I don't want to derail anything. So go
Oh,
ahead.
thanks. It's also that when this is brought up, I need to think really hard, and it probably will derail me.
Okay.
But I would actually like to get more of a solid handle on it, so maybe we should talk afterwards. Okay. So the best point in the space, the point of maximum likelihood, we're going to call that x equals 0. No points are above it. Okay. There will be somewhere in there with a point with the worst likelihood. Actually, yeah, really, it's usually a contour, which still has measure 0. But just glossing over all of that. The worst point in parameter space, all the other points beat it, so that's going to correspond to x equals 1. Now, because this x factor, what fraction of the points are worse, sorry, what fraction of the points are better, is a rank. The prior distribution over this space, in terms of rank, corresponds to a uniform distribution for x here. So the more formal definition of x is that x as a function of L, this is a rank as a function of a likelihood, is the fraction of the prior probability that has a likelihood greater than the likelihood that we've specified. So if I was thinking of a likelihood value of 0.5, I could imagine calculating the prior probability, or the probability according to the prior distribution of the likelihood value being greater than 0.5. And that would be the x of 0.5. So this is the prior probability times a function that's 1 if the likelihood is greater than L. If you want to think a bit more loosely, instead of thinking of prior probability, you can think of volume. So if the parameter space is 3D, is the 3D space of this room, and there's a high likelihood region over here, say, then if I'm thinking of a likelihood value that's really low, the fraction of the space that's above a really low value is really high. So for high volumes, so for low likelihoods, we have high volumes that have likelihood above. And as we shrink, as we find regions of higher likelihood, the fraction of the space that has likelihood above that gets smaller and smaller. So we have high volume regions with low likelihood and low volume regions with high likelihood. And the x is prior volume. Okay. So if we are able to generate any points in our space, we can measure their likelihood. So any method I do, I can just pick points at random. I would know the values of their likelihood, so I would know their y position on this plot here. The hard part is knowing the x value. So if we know, so if we get some points and we know their likelihoods, we know where they are in the y dimension here, but we don't know where they are in the x. One thing we do know is that they should go in order. If lower likelihood points will have higher x values. It turns out that you can measure the x values of the likelihood points using the nested sampling procedure, and I'll just I'll present the algorithm itself, which actually sounds rather easy compared to understanding what it's doing. So this is the procedure, and this is what I've got implemented in code. And what this will do is we'll generate a sequence of points in parameter space with likelihoods that are increasing, and there'll also be a recipe for estimating the amount of prior volume that you've got as the likelihoods are increasing, so decreasing amounts of volume. And then you can do the integral numerically. So the algorithm starts out by you define a number of particles or walkers or points that you're going to generate in parameter space, n, and then you generate them from the prior. So the marginal likelihood we're trying to do is an integral with respect to the prior. So we start by generating points from the prior. So most of those points are not going to fit your data. They're going to be crap. But what you do is you find the worst one, the lowest likelihood, the least good fit, and you measure its likelihood. You call that L star. And then you know, so say n was 100. You're generating 100 points from the prior, and you're finding the worst one. Therefore, you know that at least roughly, the fraction of prior probability, or the fraction of the volume that beats that likelihood, is 99%, because you had 100 particles. You found the worst one. Maybe its log likelihood was minus 1,000. Then you know that since 99 out of 100 points beat, drawn from the prior, had likelihood greater than minus 1,000. You can guess that the value of x is roughly 0.99 for that point, and that's exactly what you do. So you generate all your points, find the worst one, find its likelihood, L star, and then you write that to disk or something. You find first iteration, my worst likelihood was minus 1,000, log likelihood minus 1,000. Then you need to generate new points. You're going to forget about any region of the space now that's worse than that point you just discarded, and you would need to generate a new point that has likelihood above that, because you don't care about those bad regions anymore. So you then replace that worst point with a new point drawn from the prior, but you have to restrict, because you're no longer interested in low likelihood regions below L star, you have to restrict the domain that you're generating the point from to the region where the likelihood is above the point that you just discarded. And this is the kind of hard part of nested sampling. This is in general a hard task to do, but there are some pretty quick and easy ways to at least do an okay job of it. So the algorithm repeats these last two steps over and over and over again, and each time you do this, you're basically saying you're discarding a known fraction of the space. So if you start with 100 particles, you find the worst one, you say, okay, that's 1/100th of the space and it had that likelihood. Then you generate a new point above that. You're now looking at 99% of the space now. You find the worst one there, you discard it, and you say, okay, that one is going to represent 1% of 99% of the space. And you keep doing it. Each time you do it, you're cutting down the volume by a factor of 0.99. So your volume is going to shrink geometrically as you do this. Okay. Another point to remember is that the discarded points, this one, that each iteration is the worst likelihood point, that actually is the output of the algorithm. It's not the points that remain that are the output. It's just the points that are selected as the worst and written to the disk.
So,
yeah.
How does this help in a situation where there are multiple regions of, right, so your spider case?
Yeah. The reason why it helps is that it's just multiple initial conditions, but it's multiple initial conditions that get you to so you can have multiple initial conditions in MCMC, right? You can have you can just start your chain in lots of different places.
Okay, I see what it is.
Okay, cool. I think it might be worth explaining for everyone else though. So for multiple chains in MCMC, you might find that you have these different modes. But one thing you won't find from just running different initial conditions is how important each of the modes are. To do that, you need some way of going between them. With nested sampling, you end up with a bunch of points that you can prove, at least in certain limits, are a valid sample from the posterior distribution. And so it's going to give you lots of initial points. So some of them will end up in one mode and some of them will end up in another mode. But in a way that, at least in certain limits, it's guaranteed to represent the two modes with the correct probability. So the fraction that land in one mode and the fraction that land in the other will be the fractions that they should be. Whereas in just doing different initial conditions, that's not true. So the hardest part of nested sampling is how do you generate a new point from the prior but restricted to a volume that's very small and that has high likelihood. And this seems really hard because as the volume is shrinking geometrically, after a fair number of iterations, the volume that you're trying to sample from can become exponentially small. So you might be trying to find a new point in a region of the space that is smaller than the whole space by a factor of e to the power of 100. So a method that is terrible would be to just generate points from the prior and then see if the likelihood is good enough. And don't do that. The easiest method to do, which was the original suggestion in the nested sampling paper, and it works better than it sounds like it's going to work, and that is that you take one of the other points that wasn't the discarded point, and you know that by definition their likelihoods satisfy the constraint that you need to be satisfied. Because they weren't the worst point, so their likelihood has to be higher. So the procedure is that you can just clone one of those points that automatically satisfies the constraint, and then you can do a little MCMC run for a few thousand iterations or something, trying to sample the prior, but you just reject any proposal that the likelihood that would take the likelihood below the constraint that you need to satisfy. So that's the method that I've implemented in the little code that is in the repository.
Why can't you just take the next worst point?
As opposed to you could say that my rule for generating a new point is to take the next worst one and evolve from there.
But why do you have to evolve? Why can't you just take that? You have your 100 samples. Why can't they just define this little circle?
If you had 100 samples and they never moved, and you just discarded the worst one and then the next worst one and the next worst one, you would never get them into the places where the likelihood is high that eventually dominates the integral. So that would be something similar to just sampling the prior and averaging the likelihood.
You would just have 100 samples?
You would just have 100 prior samples and that's it. And they would never move. Yeah?
Just clarification, when you say reject proposals likelihood below L star,
yeah,
is that within the MCMC or after you've run the MCMC?
Within the MCMC.
Okay.
So you can, you're doing MCMC, but instead of trying to sample the posterior distribution, so making your acceptance probability the ratio of prior times likelihood at the proposal to the current point, it's the ratio of prior times an indicator function that defines the acceptance probability.
Would it be wrong to do it after the fact?
It would at very least be extremely inefficient, because if you start from a point that satisfies a really tight constraint and then you start moving around trying to sample the prior, if this has volume e to the minus 100, that you're going to go out of it and you're never going to come back in.
Right, but you can also get stuck in a mode if your constraint is too tight.
That's true, and getting stuck in modes does happen with this version of the algorithm. The cheap way to, or not cheap way, the expensive way to overcome that is use more points. Yeah?
Is there a requirement that you have to uniformly sample the remaining
uniformly sample it. What do you mean?
We
You need
usually
to
use
generate from the prior, which in many cases is uniform. Sorry?
You need to choose from the choose from the prior.
Yeah. So the way
It sounded like some of those methods wouldn't do that.
some of which methods?
Like choosing the lowest, starting from only
The second lowest.
Yeah.
If you started from only the second lowest and ran MCMC for a really long time and assumed that you never got separated from the important modes, then that would be okay. But it's probably better to initialize from a random point rather than the second lowest. So I think I'll just show you a little bit of the code just to get you acquainted with it. A lot of it will look quite similar to Phil's code. So if you look in the transit model.py, this is just a set of functions that define the log prior, the log likelihood for the model that I've been discussing in this presentation. So this transit model.py, there's a number of parameters, which is 4. There's a data set that I'm going to use to evaluate the log likelihood, and just some summaries of the data that happen to be useful for later. In nested sampling, you start by generating points from the prior. So I've written a function called fromPrior, which just generates points from the prior. So generates A, B, T, C, and W from the priors that I had on the slides, and puts them all into an NumPy array. There's a function for evaluating the log of the prior density, and since we're just using uniform priors, all that's going to do is check if any of those go out of bounds and return minus infinity if they do. Otherwise, it just returns a constant. The log likelihood is pretty standard as well. Takes as parameters the argument, the 4 parameters, computes the log of the Gaussian density, so this is basically -1/2 times CHISC with some prefactor terms. And the other thing that I've defined here is a function proposal, which is going to define how I move around, how I propose new values for the parameters to do the MCMC, how to move around the parameter space. Now what Phil was doing was he had a multivariate Gaussian proposal where in all the dimensions you would update all the dimensions at once, so all parameters at once. I prefer to update one parameter at a time. So one difference between this and what Phil was doing is that I'm choosing one of the 4 parameters at random to change while keeping the others fixed. And this is also a valid proposal that you can use in MCMC. It generalizes better to high dimensions than what Phil was doing. The other thing that's really important, especially in nested sampling, because the distribution that you're sampling is changing with time, it starts out being the prior, which is usually really easy and you can take big giant steps, and it ends up later on being some really constrained small distribution where really small steps would be more appropriate. Instead of trying to tune and do like as a function of this distribution, how should my step sizes decrease, that would be really annoying. So instead I do this thing where I randomize the step size every time I do a proposal. So here I've got, I'm adding a perturbation, a Gaussian perturbation to the parameter that I've chosen to move. And I've also got a kind of rough size estimate of how big jumps are going to be for each of the parameters, and those are defined at the top. But then I'm also multiplying that step size by this factor here, which is a factor that will sometimes be around 100, and it'll sometimes be 10 to the minus 3, and sometimes 10 to the minus 5, and so on. So I'm sometimes taking steps that are really big, about roughly the order of magnitude of the prior, because at the beginning I'm sampling distributions that look like the prior. I want to take big steps. And later on I'm wanting to take steps that are really small, and I'm just hoping that 10 to the minus 6 times the prior width is not still too big. So this is a little bit inefficient in that, for every distribution there's going to be an optimal step size. and we're probably missing it by a couple of orders of magnitude. But at least some of the time we'll be doing an appropriate step size. And I'd rather have a factor of a few performance hit in doing this than have to do 100 runs to tune everything. It's a trade-off between, yeah. I don't like tuning. I never tune much. You have to tune something. So the nested sampling code itself lives in nested sampling.py, and it just imports the functions from the transit model. And then you define some parameters of the algorithm. So you have to decide how many particles you're going to have, and here I've got 5. Generally more than 5 is actually better, but I want it to run in reasonable time, so I'm doing 5. The number of iterations you're going to do, so how many times you're going to do this loop of throwing out the worst particle and generating a new one. And that's very problem dependent. In some problems you'll need this to be very high, and in some problems you won't need that many. I'll talk a little bit about diagnostics of understanding how many you need. The other tuning parameter of nested sampling is how many MCMC steps you're going to do for each nested sampling iteration in order to try and generate a new independent point. And I've just used 10,000 here. So I'll just very quickly run through the code and point at the most important parts and relate them to the algorithm. So first we're generating n points from the prior, so I'm just putting them in a list. So using the from prior method, and then just putting those objects in a list, and then evaluating the log likelihoods of all those points, because we're going to need to find the worst one. I'm also just making a storage array to keep results in as we go. So the main nested sampling loop, I'm just going to go for steps, and I don't know, Python experts might be able to see that my native language is C++, because I always want to write like for int I equals 0, I less than n, I++, and I just translate that literally into Python a lot of the time. So what we're doing every time in nested sampling, you just find the worst point, lowest likelihood, scrap it, but keep its information somewhere, and then generate a new point, make sure that its likelihood is above the one you just scrapped. So that's all you're doing. So find the worst particle, lowest log likelihood, save its information somewhere into this keep array. And then I look for, to initialize the MCMC run to generate a replacement, I'm just looking for one of the other points at random, making a copy of it. And then I'm doing MCMC for a little while, trying to sample the prior distribution, but with a restriction of keeping the likelihood above that threshold defined by the discarded point. So this acceptance probability is slightly different from what you usually see. You usually see in the Metropolis algorithm that the acceptance probability is the ratio of the prior times likelihood at the proposal divided by the current point. Here instead we have what looks like an acceptance probability that's based only on the ratio of the prior densities. So it's this log A is log P nu minus, so it's the proposed value of the log prior minus the current value of the log prior. And then there's an extra condition that the log likelihood has to be above the threshold. So this part looks like the standard Metropolis Hastings, but without any likelihood in it, just the prior, and then there's the hard threshold of log likelihood. And then if that's true, then you accept. So in order to do the integral and to estimate the x, so the x values of these points that are being generated, the discarded points, to do the integral for the marginal likelihood, you need to know the x value, which is what fraction of the space are we looking at? What fraction of the space has likelihood above this value? And in the skilling paper, there's an easy deterministic approximation, and it basically says that if I have 100 particles and I do 100 iterations of nested sampling, the fraction of the space that will restrict me by is down to 1 over e of the space, because it's geometric. If I have 1,000 particles and do 1,000 iterations, that'll also mean volume has gone down by a factor of E. And so just using that as a guess for the x values of all the discarded points works pretty well. And then there's just some plotting, and calculates the marginal likelihood and prints it out, and things like that. And also makes posterior samples. I won't go into detail about the posterior samples. Yeah?
So, which point seems to replace the discarded point? Is it the last point in the MCMC one?
Yes. Yeah. So when you discard the discarded point, you clone a new one, and you do an MCMC run. It's the end point of that is the replacement. Yeah. Because you hopefully have run for a long enough time that the end point is independent of where you started. And if you took a point from earlier on, that would be more correlated with where you started.
Right.
Yep.
Do they have to be independent? Or is it just the likelihood constraint? Is it just enough?
It depends. So the theory about the accuracy of nested sampling and its convergence properties all assumes that the new point is independent. And when there's a formula for computing the error bar on log z, which is based on the assumption that they're independent. So all that will happen if you do a fairly short MCMC run is your results might become slightly wrong in a way that's bigger than the uncertainty that's reported. But you can do standard things to check convergence, like do runs of different sizes and things and make sure they're all agreeing, things like that. Actually, sometimes it's surprising how few MCMC steps you can do and still get a somewhat accurate answer. Depends on the problem.
And a note for people who are playing with the nested sampling code.
Yes?
If you add, so I think the default for OS 10 matplotlib is interactive mode off. So if you add plot.ion,
Yeah.
like an ion, parentheses at the top, you'll watch the thing go.
Isn't that in the script?
It was not.
Oh, I thought it was.
Because I was like, oh, there's a plot at the end. But
Yes.
yeah.
Yeah, probably.
Why did I not?
Okay, I'm going to run it right now anyway. So, okay. So I'll briefly talk about what these plots are as well, because they're very helpful for diagnostics. Okay. So this, as you can tell, this is a fairly non-sophisticated script with not very many labels on here. But what we're looking at on the top plot is each time I do a nested sampling iteration and discard the worst point, I know its log likelihood, and that's on the y-axis. So the leftmost point, as the algorithm goes on, is the most recent discarded point and the log likelihood of it. And I made some attempt to scale the y-axis so that that the y-axis isn't dominated by this big transient thing at the beginning. So as the algorithm proceeds, we're plotting points that are equally spaced in terms of the x-axis on here, which is actually log of the volume, log of the remaining prior volume as we go. So prior volume is shrinking exponentially, log of prior volume is going linearly down, and so we're getting equally spaced points going out to the left. And log likelihood is strictly increasing. Now with the bottom plot, what we've got is a measure of how important each of those discarded points is with respect to if we are interested in the posterior distribution, which we usually are. So if you take prior samples and if you take discarded points from the beginning of the run, they tend to have very low likelihoods, and they shouldn't contribute to anything that you care about with the posterior. And actually, if you wait for a really long time and go all the way to the left, you find the maximum likelihood point. And the maximum likelihood point is actually really unimportant for the posterior as well. And the reason is that, well, the maximum likelihood point is a point. It has high likelihood, but it has really low prior probability. So somewhere in the middle of this run, there's a peak in this posterior weights, and that's the point at which the rate at which prior volume is shrinking and the rate at which likelihood is increasing, the product of those hits a sweet spot, and those are the points that describe the posterior distribution. So with the tuning parameter of how many steps to take, or how many nested sampling iterations to do, that was this one, steps. That's problem dependent, and what you want to do is you want to run for long enough so that you see this peak and that you basically get the whole peak, because points down here have really low posterior weight, and we might assume that if you kept going you're not going to see another peak. Sometimes you might, but usually you won't. So in this particular problem we didn't need to go past about -30, so the number of nested sampling iterations we needed to do was about 30 to shrink by a factor of e to the 30, multiplied by the number of particles, so that should probably be n in general instead of 5. What happens if this is too small is that you only get part of this diagram and you end up missing all the points from and you'll end up getting only like one particle to supposedly represent the posterior distribution.
Brendon, could you say something about that? How smooth that lower curve is?
Yeah.
Does that represent somehow how accurate your sampling has been, or is that not that important?
It's more a function of how many particles you're using.
But that's also
which is also to do with the accuracy. Yeah. So if the higher particles is more accurate but slower, so all the usual trade-offs you would expect. And actually the error in the log marginal likelihood that you get goes down with square root of n in all the usual ways. So one output that you should see at the end when you close the plot is that I've printed an estimate of a few quantities. One is the log of the marginal likelihood, so it's about -163. So the probability density of the data given the model is about e to the power of -163. But that number on its own doesn't help you very much. What you really need to do is be comparing this to an alternative model, which we might just do a little trivial alternative model quickly. There's another quantity which is interesting, and I think it's actually more interesting than the marginal likelihood. It has been called the information. And for those of you who know probability theory or information theory, information is the KL divergence from the prior distribution to the posterior distribution. And what that quantifies basically is it has a very natural interpretation as how much was learned about the parameters from the data. So in this case it's 17 nats, and nats is just a unit. And what 17 nats means is that basically we have ruled out 1 minus e to the power of -17 of the possible values for the parameters that we had in the prior by going to the posterior. So for example, if you had a data set for which and a model for which the information was 1 nat, that would mean that your posterior basically occupied 1 over e of the prior volume.
If you're talking about information, wouldn't bits be a more natural way to characterize the amount of it?
So the question was, wouldn't bits be a more natural way to quantify it? I don't know. I got used to nats.
But if you say the same thing that you just said about prior and posterior volumes, instead of 1 over e, you use the base of the...
Yeah, you'd use the base of the logarithm.
So it would be half.
So it would be half, and it is actually a lot easier to talk in terms of half.
Yeah.
So the information, if you convert it into bits, so you just divide by, what is it, log base e of 2, or multiply by it, I forget what. So if you get an information of like 100 bits, that means that your posterior is occupying 2 to the minus 100 of the prior volume.
And 1 bit would be...
One bit would mean you ruled out half the possibilities and maintained the other half, which is very nice to think about. One thing that's a bit annoying about information, though, that you get out of nested sampling, is that this measures how much information you learned about all the parameters that you had, not just the interesting ones, maybe. So if you have some nuisance parameters, this also includes how much was learned about nuisance parameters. And
this is very related to what we were talking about at coffee with Pop.
Yes.
Who was pointing out that for many of his problems he has lots of parameters where he doesn't know how to assign prior.
Yeah.
And so here you are, extracting information from data. A lot of that information will be about those
about nuisance parameters, yeah.
You will learn a ton going from a very uninformative prior that you assign to a parameter you don't care about. You'll constrain it with the data and lots of information will appear, but you might not care about that.
Yeah, and actually in the standard situation where you have a very broad prior and the Gaussian likelihood function, and in the limit where when you make the broad prior really, really broad, the marginal likelihood keeps going down because that prior didn't predict the data very well because it wasted all its probability on values that don't fit the data. If you do that, the marginal likelihood can go down basically to 0 in the limit that it becomes infinitely wide, the prior, but the information goes up. Because if you imagine you had a uniform prior between minus 1 trillion and 1 trillion, and then you learned that the value of the parameter was 1.3 plus or minus 0.1, you ruled out a really huge fraction of the possibilities, and so the information value would be really high.
So one way to say this, because low information goes with high evidence goes with low information.
Yeah, that came up last night.
So in science, you cannot lose. Either you find strong evidence for the model that you assume, and you're happy, or you're surprised and you have a lot of information.
And then you're happy.
Yeah. You're happy. So you cannot lose.
Good.
Just small, this term information, there are lots of precise versions of the term information, and even in statistics, this is like a specific...
This is one thing.
Yeah, so for me, I just don't want somehow the idea that in this particular setting, the people that take away is that information
means just this.
Yeah.
I would so there are lots of things with the word information attached to them, and you shouldn't mix them up. I would actually argue that this is the one that I would like to attach the word information to.
Because you're Bayesian.
It's the
yes.
from your prior beliefs to your posterior.
I mean, even if you want to use information, it's like the information that I gained by doing the analysis. I want to add some extra words. It's not, somehow.
True. And it's
there's there's an information metric that's going around.
There's a full definition. It's a mutual information. Is that right?
Mutual information is a different thing. Mutual information is the
Also, the scale divergence isn't even symmetric, right? And most of the other information things are symmetric. So just whatever. People should be aware.
There's lots of stuff with the word information, but this one, what mutual information is the expected value of this before you knew the data. So if you have defined a prior distribution for your parameters and a sampling distribution for your data, and you don't know the actual data yet, but you want to quantify the expected value of how much information you'll get in this sense, that's the mutual information, which is a quantity and information theory.
So this is information gain, right? Is that correct? If I Wikipedia this,
expected information gain, I would say, because it is possible for
the one that you were originally talking about, the one from prior to posterior for this data set. What's the exact term?
I don't know.
Yeah, it's totally well defined. Yeah,
right.
You don't have to use words like evidence of information or like knowledge or goodness. Yeah.
Good. Yeah.
Good. So the KL divergence between the prior and the posterior.
Yeah.
And I think on the Wikipedia page that's synonymous with information gain.
Okay.
But only on that Wikipedia. But KL divergence, you're saying callback Liebler divergence between prior and posterior is the precise statement.
I mean, at least it's fully well defined.
It is, yeah. If you just say, oh, the information is this, to anyone who's not like one of the three people who use the word information to mean that, then you're introducing ambiguity. Yeah.
How would you use it?
Sorry?
How would you use the value of information? Would you compare it to data sets? Can you use that somehow to see if their model is good?
Not really. I think the only application it has is for you to look at it and go, wow, that's cool. I think mutual information has an application in experimental design. So before you get the data, if you're considering different kinds of experiments that you might do to constrain the parameters, you might want to optimize the expected value of that.
But for example, you have two data sets at your disposal.
Yeah.
You do the analysis with both.
Yeah.
And you see that you cannot combine them for some reason.
Yeah.
You should choose the one that gives you the highest information.
That would be a heuristic that might make sense, if for some reason you can't combine them.
Since we're stuck on this, can I make one quick comment? Is that we were talking earlier about priors and things like that, and
Yeah.
I mentioned that there's this class of both objective priors where it's like a procedure that you apply to your model that gives you a prior that's suited for your problem. And the way the reference prior is defined is you find the prior for which the expected information gain going from prior to posterior is the least. So it's like the least informative prior, so in some sense. Right? So you're trying to like find something where your inference is not being driven by the prior but by the data. So that's it. So it's a well-defined thing. You search over priors and you find this thing. And so it's and that's something you can do before you actually have data, because it's always done on the expected information gain. So that's so this whole thing is something.
Yeah.
And in fact, that mathematical formalism is sort of the high-level version of what happens in what astronomers do all the time, which is that they go ahead and assign uninformative priors because they somehow want to look at the information that's present in the data and get inferences that don't depend on the prior.
But what astronomers write down is rarely the reference prior.
Uninformative priors are highly informative.
Right?
No, it's
Yeah,
they're not. I mean, you're completely fooling yourself if you think like putting a uniform prior is uninformative, right?
Yeah,
so the reference prior is how you put an uninformative prior on your try. And so somehow this idea that you're putting an uninformative prior is basically like totally misleading yourself.
Yeah. We saw some of this yesterday, Kyle, with the difference between uniforming the parameter and uniforming the log of the parameter, but we didn't get into the reference prior.
Yeah, and then high dimensional problems is like super hard to do, right? So
Yeah.
And these reference priors are rare to compute, but at least it's a conceptually nice thing to think about.
Yeah. So reference prior, in my talk yesterday, or whenever it was that yesterday? I can't believe it. I mentioned this division between objective priors and subjective priors, and what we all really do, which is just choose things. So a reference prior is one example of they're called objective priors. It's one where you state some kind of principles and then you derive a prior from those principles. You might like or not like the principles, but that you have your priors are derived rather than asserted. Okay, so it's almost lunchtime, so I think just to finish up, I might very quickly show you how you might do a model comparison very easily with this. So let's just go and change the model in a kind of trivial way and run the nested sampling again and get the log evidence for the changed model. So I'm going to change the model to something that is actually it's a nested situation. So I'm going to change the model to something that already exists in this parameter space that we've set up. And in general, I don't recommend that if you're in that situation with nested models that you do separate runs with nested sampling in order to compute the evidence for one or the other. In general, I would say if you can unite your two models into one parameter space, just do Bayesian parameter estimation on that space and don't do this separate nested sampling for this, and this is generally less efficient. But since it's easy to do, I'm going to go into my log likelihood and I'm just going to comment out the bit of code that puts in the transit, and we'll get the marginal likelihood for a no transit model. And of course this depends on all priors and things still. I realized when I was doing this earlier today that there's no, in this code I haven't printed out any messages about what the acceptance fraction of the Metropolis Hastings is when you're doing the little MCMC runs. And actually this code unfortunately crashes if that is 0. So on some problems, if you go for too many iterations and you're sampling some tiny little distribution like this and you're actually rejecting all your MCMC moves, it just crashes inelegantly and you don't get a result. So I apologize for that feature of this script, but this is on GitHub, so someone can submit a pull request if they want. So I'm just going to run for, I'll try and compress the prior volume by a factor of e to the power of 10, and the number of iterations you need to do to achieve that is proportional to the number of particles. And we'll just remember that the log marginal likelihood was minus 163 for the correct model. So our discarded points, likelihood is increasing, prior volume is decreasing, that's the x-axis is log prior volume. Posterior weights are increasing, so we still are finding points that are more posterior E than the previous ones. That's a technical term. And what we're hoping to see is that we've got the correct number of iterations so that we go over a peak and come back down the other side. And it looks like that's happening. And when it gets to 10, it'll stop, and then I can print out the results. Okay. So, oh, did I go further than 10? What did I do? I didn't save. Oh my goodness. Okay. Sorry about that. You know, let's just do less MCMC steps, make it go faster. Much better. And of course I could have written it in Julia, but Eric's not here anymore, so it doesn't matter.
How do you do that for loop on B?
Sorry? Yeah. One thing about MCMC is that I'm constantly writing for loops, and but you can't vectorize MCMC. It's inherently loopy. Okay, so we got that peak. Great. And you'll notice that this peak happened a lot closer to log x of 0, so we didn't have to go as far inwards to get the important posterior probability points. And that corresponds to this information value being quite small. We have here that the log of marginal likelihood is minus 354, and in the previous one it was minus 163. So the Bayes factor for the true model over this one is a factor of about e to the power of 180. And so a lot of the time people worry about, you know, I need to do enough computation to get my marginal likelihood correct or my log marginal likelihood correct to within about plus or minus 0.2, because that's how sensitive I am to slight differences in probability judgments. But actually you can show that in high-dimensional problems, or problems where this information value is really high, where the prior is like this and the posterior is like a really super tiny thing, the prior probability of getting a data set for which you would need accurate marginal likelihoods to within such a small accuracy is exponentially small. So in practice, log marginal likelihood differences are not of order 0.2. They're usually much bigger than that. There's just one thing I'd like to point out before finishing up, and then we can eat, is that the shape of this curve, this top one, log likelihood versus log prior volume, tells you something about the structure of your problem, and in particular it tells you whether there's a phase transition. So phase transition was this plateau with a spike on top of it situation. If you do that, if your problem does have that, then I think one occurred here by chance. I'll zoom into it. Then the plot it goes like this. It looks like it's approaching one kind of likelihood value, and that's when all the discarded points are in the plateau. And then suddenly it starts going up the narrow part, and the log likelihood starts increasing rapidly again. So if this curve on the top has a shape that's like it's plateauing and then it accelerates again and plateaus again, then there's a phase transition, and that means that methods that aren't nested sampling will give you the wrong answer for the marginal likelihood in general.
Although, I mean, it could be arbitrarily far off, and at some point you have to choose to stop nested sampling, so there's still a chance you can miss it, right?
Yeah. So if you read the nested sampling papers, it's a lot of it's put in statistical mechanics language where they talk about the different phases as like water and ice and steam, which in data analysis doesn't make much sense. But I think the important point that Kyle was pointing out is that you might see this peak and think, oh, I'm done. I've got my posterior samples now. I don't have to go any further. But you can't really prove that if you hadn't gone further, you wouldn't see another peak that ended up being more important. In data analysis, you can often convince yourself that another peak doesn't exist. For example, if all these points in my posterior sample had reduced chi-squared of about 1, then it's not that I'm going to find some extra amazingly fitting things if I keep going. I think we'll finish there. Thanks for your time. Yeah, there was a question.
Two things. One, so I'm a little bit confused by your choice of always randomly taking a random step size in your MCMC.
Oh yeah, that's one of my favorite subjects. I don't know the width of the posterior distribution, that's why I'm doing the calculation.
Right, but it seems like you would be very likely to take very poor steps very often.
Yeah, the
which
fraction.
Which means you're likely to not actually move that point.
So acceptance probabilities for these moves, they depend on at what stage of the algorithm you're at. When you're at the prior, it's basically 100%. Especially if you have a uniform prior, if you wrap around it will be 100%. It goes down, and in most problems this my shrinking factor of like 10 to the minus 6 of the step size, I always end up with an acceptance probability of at least 10% by the time I'm sampling in the posterior important parts. So it's probably a factor of, I don't know, it would be interesting to quantify this, maybe a 10-minute hack. How inefficient is this super heavy-tailed proposal compared to the optimal Gaussian step size? And I think it'll be a factor of few. I'll obviously lose that because the optimal thing is optimal. But the performance of this will be much more robust to not knowing the optimal step size. And I don't like tuning. I just want to do this and do it once.
But it's good to know that you're sampling the prior there under the likelihood constraint. So you're not that if you're actually sampling a likelihood where the likelihood value itself differs a lot, then I would imagine that it's a little bit more important than when you're just sampling the prior. If you're just within the likelihood constraint range, then the prior values are often just the same if you're sampling uniform or whatever. So it should be less important then, right? You just have to move in some way.
I don't know what you're getting at with that.
Well, so typically your acceptance rate in high dimensions should be about 24%.
I've heard that, yeah.
Right, for MCMC.
Yeah.
But that's important because your likelihood is changing. But if your prior is sort of flat-ish, then you're just
sampling a constrained uniform distribution.
Right. Is that the reason why this works well?
No, I use the same steps to sample the posterior as well. And then it's not optimal, but I don't have to tune. I'm willing to pay in computer time. Gives me time to check Twitter.
And then the one other question, which is a question in the comment, is that I looked at this and I was like, wow, this has got to be really hard if every step is a big calculation.
Every step is a little bit of MCMC. There have been some people who've done...
Because I looked online and there is a parallel version of it where you throw out multiple things in each and apparently it's
Yeah.
mathematically valid.
There,
It changes.
okay. There are lots of, so this is the version of nested sampling with this cloning and doing MCMC is only one option, and there are other software packages with different things that try to generate a new point in different ways. So the famous one for astronomers is multi-nest. And the group that came up with that now has a new software package called Polychord, which uses something else. There are different variants of nested sampling out there, and some of them are probably better than others in certain circumstances. But I don't have that much to say about that, except that things like multi-nest are probably only good in not that many dimensions. You wouldn't want to go into even 50 or 100. But this MCMC one can work pretty well in high dimensions.
Polychord is ostensibly better.
I've heard that, yeah. I don't know the details of it.
Just as early on, we were sort of motivating this. Part of it was being able to calculate the evidence. The other part was being able to efficiently handle these
The hard stuff,
and all
yeah.
these things. And of course, there's tons of ideas about how to modify MCMC to try and do those. I don't know if you talked about it earlier, but there's another brand of all of these Bayesian tools, which is the Hamiltonian Monte Carlo.
Yeah.
And those handle high dimensions and these kinds of structures very, very well.
So the Hamilton,
It's a whole extra one. I don't know if you guys got into it, but it's
I think it's been mentioned, but not in the tutorial sessions. So
Yeah.
Hamiltonian Monte Carlo is really good for high dimensional things with the kind of curving degeneracies and stuff like that, but it can't get you from mode to mode. There are other methods that can get you from mode to mode that are based on this idea of annealing. So you see methods like with the word annealing or tempering in the title, like parallel tempering. And they can also help get you from mode to mode, as can this version of nested sampling and some others as well. There's lots of stuff out there. I think one of the most important things is if your collaborators use a certain tool, then maybe start with that one. Otherwise, start with mine. Cool.